You are lost and gone forever, now we're live. Okay. State versus path. All right. State function versus path function. So, these are about the state of the system versus the path you took going from one place to another. Okay? A state function is just a property that depends on where you are right now, and it doesn't matter how you got there. Whereas a path function is a property that depends on how you got where you are. Okay? So a state function only depends on the current state of the system, and the path function depends on the path you followed. Okay? So the popular example of this is distance versus displacement. Okay? You travel 4 miles south, 5 miles east, 10 miles north, 8 miles west, and 6 miles south. How far are you from where you started? Versus how far did you travel? Okay? So bring this up. So you start here, you go 4 miles south, then you go 5 miles east, then 10 miles north, then 8 miles west, and then 6 miles south. How far are you from where you started? Well, 4 down, then 10 up was 6 up total, then 6 south. So we have now just traveled 3 miles due west of where we started. Okay. But how far did you travel? Well, 4 plus 5 is 9, plus 10 is 19, plus 8 is 27, plus 6 is 33 miles total. All right. So wherever you are, okay, how far you are from where you started is a state function. You could take, any path you want. If you end there, you will always be 3 miles from where you started. But obviously, if you just walked 3 miles west, that would be a far different total walking distance than this much longer path. Okay, so the reason we care about this is because some things are state functions, some properties that we can measure for a system are state functions, and some are path functions. Okay? So temperature, volume, pressure, mass, energy, those are all things that we can measure about a chemical system. Those are all state functions. Okay? The temperature of the system, you drop the temperature, you raise the temperature, doesn't really matter. The temperature is just whatever the temperature is. Volume, pressure, all ditto. It doesn't really matter how you got where you are. It's just those are the properties of the system. But there are some things that we can measure that are not state functions. The two big ones, the ones we're going to work with a lot, are work and heat. Those are both path functions. How you get from state A to state B, the work and the heat necessary to the work you have to do and the heat that is produced or possibly put into the system will change a great deal depending on how you get from one state to the other. So consider a battery. Okay, it's just one. I need another picture for this. Okay, so you have your battery. Let's say the chemical energy inside the battery means you can do, it has 10 joules of energy stored inside of it. And so what you do is you just hook up a wire going from, one end of the battery to the other. And it uses up all 10 joules of energy. And the result is just all of that energy gets wasted as heat. So Q equals 10 joules. And the work that you do, Q, lowercase q, rather confusingly, in this case means heat. W means work. So by hooking up your wire to the battery and just letting it, run itself out, you've gotten zero work out of your battery. You've, used it all up as heat. Whereas, you take your battery, same battery, 10 joules of energy, and now instead of, just wasting that energy, you hook it up to a fan, right? Now, Q, you're still going to waste some of that energy as heat. You have to. You can't get, a nice perfect system like that, but say only 2 joules of heat. Meanwhile, you get 8 joules of work out of it. So the same total amount of energy coming out of the battery, but one way it does work, the other way it's just wasted heat. So getting from full battery to empty battery, same total amount of energy. Energy is a path, or is a state function. But how we use that energy, the path we follow, determines the heat and the work coming out of the system. Okay. So heat and work are both path functions, and that makes them difficult and annoying to work with. State functions are good. We like state functions. You don't need to know the path to know the value of a state function. You only need to know the beginning and final positions. You measure it at the beginning, you measure it at the end, you know the difference between the two, boom, you're good. Okay? So we like state functions. Problem is, sometimes we have to use path functions because those are usually easier to measure. But that's a real pain in the keister, because you have to measure every single point along the path in order to really get a good measure of a path function. And that's hard. Okay, you have to take constant readings. You have to be reading constantly all the time. So in physical chemistry, thermochemistry, we use our brains to try and find a way to turn path functions into state functions. Because state functions are powerful, but they can be hard to measure. Path functions are easier to measure, just in terms of what's going on, but they're less informative. And when I say they're easier to measure, I mean that usually it takes a simple setup. And you can measure heat by measuring changes in temperature. You can measure work in various ways. Measuring energy is what? Okay, so we measure energy changes by measuring heat and work, but the thing is, heat and work are path functions. So what we do is we try to get clever about the way we set things up, because if you set it up right, you can find a way to turn a path function into a state function. So that is a lot of theoretical. That's a lot of brain power has gone into thinking of ways that we can constrain the system to force it to be a certain way, so that a path function turns into a state function. And people have gotten pretty darn clever about that. So those are path functions versus state functions. A path function depends on the path you follow. A state function does not. Okay? And the big examples of those are temperature, volume, pressure, mass, energy. Those are all state functions. And path functions are, well, the big ones are work and heat. And a lot of physical energy, a lot of physical chemistry, not just physical chemistry, but also physics. There's been a lot of work into, a lot of thought, a lot of brain power has gone into understanding work, heat, and energy. Why? Because of choo-choo trains. The 19th century was all about making better, bigger, more powerful, and above all, more efficient engines, so that they can get more work out of them. All right, but notwithstanding, that is the end of this set of slides. Those are, part of setting up you can see we have a lot of slides going on, a lot of sections going into Chapter 8. So tomorrow I will go ahead and do several more sets of slides in order to get us on a firm footing for Chapter 8. We have 2 weeks for Chapter 8, and then there's going to be a test on 7 and 8, and we'll start Chapter 9. In any event, I wish you luck, and enjoy your Saturday evening.